So what are the two cases that we sort of didn't talk about yesterday? Because if you were astute enough, you should have realized, hey, there's something interesting about all these functions that we were sketching yesterday. They were all two specific types. When the degrees were the same, and when the degree was bigger in the denominator. There are two other situations that we need to talk about. So today, we're going to talk about how do we sketch functions where the degree in the numerator is bigger in the degree in the denominator. Yes, we did talk about those horizontal asymptote rules. So if you were to break out your notes and look at your chart, you would go, "Hey, you said in these cases you have no horizontal asymptotes," and that's true. The second type or second case we're going to talk about is when you can simplify. I did say yesterday, hey, the very first thing I would do is factorize everything just to see if anything cancels out, just in case things simplify. But, every single one of the questions I gave you yesterday didn't simplify. So today we're going to look at, well, how does that change our graph? So I think the easiest way to see this is just to, look at the graphs. So what I did was before the lesson, I just went on Desmos, and please tell me I didn't delete the, there we go. I went on Desmos, and I sort of just made some random rational functions. So for those guys who are in the back who may not see the functions, the first three examples are some of the things that you probably saw yesterday. This is an example where the degrees were the same, right? So this was our stereotypical rational functions. It has a vertical and horizontal asymptotes. You can see that. The next example is an example where the degrees are the same, but they're quadratics. Again, it looks pretty funky. It's all different. But again, if you zoom out, we can see that it has a horizontal and vertical asymptotes. And then the last example is, what if the degree is bigger than the bottom? Again, we have horizontal and vertical asymptotes. In this case, the horizontal asymptotes is 0. In each of these three cases, let's do the first one here. The idea of an asymptote is where the graph is trying to approach at the far, far extreme values of x's. It is the rational function's equivalent of end behavior. So you can see in this first example, if you are in the very, very far back here, you can't see the function. We have 2x minus 5 over x minus 3. The rule was, if the degrees are the same, the horizontal asymptote is the ratio of the numbers. And indeed, if you zoom out far enough, and you only look at the far left and the far right, it looks like a flat horizontal line at y equals 2. And that's going to be the same no matter what. Here, according to the rules, it should look like y equals 4/3. And indeed, at the far, far left and right, it looks like a flat line. This example looks like a flat line at the far, far left, far, far right. So let's go ahead and take a look at what happens when I make the exponent bigger on top. What happens at the far ends? A pretty funky looking graph. And if I zoom out, it looks like at the far ends, he does follow a line. So we still have asymptotes. That's true. But the difference here, he's not perfectly horizontal. He is at an angle. We call those slant asymptotes because it literally is an asymptote that is slanted. So that's the big idea, which isn't a big idea at all. That's the only difference between today's material versus yesterday's material. Right? So the idea is, if the degree in the numerator is bigger than the degree in the denominator, you do not get any horizontal asymptotes. There's no horizontal asymptotes, but you have a slant asymptote. Right? That's all fine and dandy. Like, okay, that's cool, Mr. Bo. I can see that in Desmos. Of course, the bigger question is, well, how do I find that slant asymptote? If this was a quiz or a test on Thursday, and I asked you, hey, find the slant asymptote, you'd probably be interested in knowing how to do that. Well, let's go ahead and talk about this. Again, slant asymptotes only exist when the degree in the numerator is bigger than the degree in the denominator. So technically, we have an improper fraction. That's equivalent like saying you have 9/2, right? Bigger number on top. Improper fractions, you can always divide. So that's the idea. To find slant asymptotes, simply divide and keep the quotient without the remainder. So for example, let's go ahead and attempt to graph this weird slanted asymptote by hand. So we're going to sketch that same function there. So example, sketch f of x equals, and his equation was 2x squared minus 17x's plus 8 over 6x plus 3. Right. So that was this very equation I typed into Desmos. Hopefully you'll notice that the process is like 99.99999% the same as yesterday. Step 1, I want to simplify everything if possible. So simplification means factoring. So I'll go ahead and see if I can't factorize this guy. Hint, I picked this example, so I made sure it factors. The denominator factors into a 3 times 2x plus 1. And then in the numerator, if you factor it correctly, 2x and x, that should be a 2x minus 1, x minus 8. Right. And then I'd see, hey, can I simplify? Can I cancel stuff out? Oh, gosh darn it, I can't. Right. So you just go through the motions, find your special characteristics, your x-intercepts, your y-intercepts, asymptotes, the whole shebang, in any order that you want. Let's go ahead and do the x-intercepts first because, I don't know, I feel like it. That's what I did yesterday. That's setting the top equal to 0. Since we factored it, that should be pretty simple. 2x minus 1, x minus 8 equals 0. So my x-intercepts are a positive 1/2 and a positive 8. Let's do the y-intercept. That's just setting it x equals 0. Now when I do the y-intercept, I actually go to the unfactored version because anything with an x goes to 0. So this guy goes to 0, this guy goes to 0, this guy goes to 0. Everyone see what's left over is 8/3? Yep. So that's why I like using the unfactored version for the y-intercept because it's super duper easy. That's just 8/3. Right. Next is the vertical asymptotes. That's the bottom equal to 0. So that's 3, 2x plus 1 equals 0. Hopefully that's pretty simple. X equals negative 1/2. And the horizontal asymptote, we've already said before, the numerator, or rather the degree of the numerator bigger than degree of the denominator means, therefore, none. Right? You do not have horizontal asymptotes. What we have instead is a slant asymptote. So this is what I mean by dividing. So to do a slant asymptote, you divide. You have to take a look at your original function and, a fraction bar. That literally says divide. So this says take the numerator and divide it by the denominator. Now, that requires us to go back to good old-fashioned long division. We did that earlier in the unit. If the denominator was monic, I'd use synthetic division, but I can't use synthetic because he's not monic. So we have to use good old-fashioned long division. So I'm going to divide 6x plus 3, dividing into 2x squares minus 17x plus 8. I'm just going to fast forward through this because the point isn't the division. So if you're a little bit weak or iffy on division, put that on your to-study list for Thursday's test. So let's go ahead and divide. 2x squared divided by 6x is 1/3 x. Multiply 1/3 x times 6x plus 3 is 2x squared plus an x. I'll go ahead and subtract. That's going to be, negative 18x. I'll bring down a plus 8, and then you repeat the process. Go ahead and divide. So that's going to be a negative 3. Multiply negative 18x minus 9. And then we'll go ahead and subtract, which gives us a 17. So everyone agrees that the 17 is a remainder, but the idea is your slant asymptote is the quotient without the remainder. So all of this work tells me that my slant asymptotes, SA, my SA is y equals 1/3 x minus 3. That's how you find slant asymptote. Literally just divide it. Whatever answer you get is your slant.
So your remainder is irrelevant?
For the slant asymptote, the remainder is irrelevant. I suppose it would be relevant if it was 0. So let me revise. If your remainder was 0, that would be significant. But if it's anything else, it's irrelevant. Yeah. And then you just do what we did yesterday. Make a sign diagram, plot all the information, graph, go home, be happy. So let's make a quick sign diagram. Only thing that goes on the sign diagram are your x values. So we have our x-intercepts and our vertical asymptotes that go on it. So -1/2, +1/2, and an 8. -1/2, +1/2, and an 8. X-intercepts are always closed. Vertical asymptotes are always open. Now here's the cool thing about asymptotes. Remember, horizontal or slant asymptotes is the quasi-end behavior of rational functions. In this case, here's my slant asymptote. So I don't have to. You could, if you don't trust yourself, you could just plug in numbers to figure out the pluses and minuses. But to figure out these end pieces here, just use the end behavior of your slant asymptotes. Y equals 1/3 x minus 3. You guys agree that's just a regular line? So in terms of end behavior, just use it informally. Up to the left, up to the right, down to the right, but down to the left. What does that line look like if we were to sketch it? What was the behavior? Up to the right and down to the left, right? So since this is a positive slope, up to the right, down to the left, I don't have to plug in numbers. I know to the left he's going to go down, and then to the right he's going to go up. Easy peasy, right? What is the multiplicity of all of our x-intercepts and our vertical asymptotes? 1, which is odd, so that means it's just going to change like crazy. Minus, plus, minus, plus. Easy, quick. I really, really sincerely hope sign diagrams are becoming easier for you. Then you just go ahead and sketch it, and then you're home free. So let's go ahead and sketch this guy. What was my y-intercept? -3. Okay, that's doable. Right. So 1, 2, 3, 4, 5, 6. Ooh, I should have made it longer. I have an x-intercept of 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6. Of course, if you're doing this on grid paper, you wouldn't have that problem. 4, 5, 6, 7. I should write a letter to Microsoft to implement a grid option here. 3, 4, 5, 6, 7, 8. Okay. So just like yesterday, I like to do my my asymptotes first. So I have a vertical asymptote at x equals -1/2. And I have a slant asymptote of this guy. So just graph it like a regular line. That was unit 2, I think, sketching lines. So your y-intercept is -3. That's where we're going to start. And then you listen to your slope, up 1/3. So hopefully a quick review of graphing lines. Start at -3, and then go up 1/3, up 1/3, so on and so forth, right? Take out your straight edge, and then connect the dots. But because this is an asymptote, it should be dotted lines. There you go. There are our asymptotes. Now it's time to sketch. And of course, the most common question is, okay, Mr. Vo, how do I start? I know it's going to be at the negative to the left, but is it below, or is it above, or is it below? And this is the second time it called me during the notes.
Yeah, because the x-intercepts are both positive.
So what they say?
Just someone's going home. All right. So how can you figure out, hey, does it start above the asymptote or below? What I do is just run through the options. If, this is a big if it is above, do you guys agree it has to follow the asymptote? But That's going to create an x-intercept, and he's going to the positive region, which, according to my sign diagram, says it's impossible. So by process of elimination, he can't go up. Instead, he has to start at the bottom. Easy peasy, right? That logic should take you 5 to 10 seconds max. Move on to the right of your vertical asymptote. You should be in the positive region, so that tells you to go up. Oh, crud, I forgot to put the x and y intercepts. So x-intercept of 1/2, x-intercept of 8. What was my y-intercept? 8/3, which is 2 and 2/3, so it's somewhere right here. Here. And then you just go ahead and connect the dots. Oh, I totally missed it. There you go. Okay. After the x-intercept, he should be negative. So I'm going to go through the x-intercept. But notice he has to eventually return to the other x-intercept. Now, this is the calculus bit. Without calculus, you're not going to know where he's going to change directions. Does he swoop like this? Does he swoop down here? I'm not going to be too picky as long as you have the general shape because we're not at that level yet. So just make sure you connect the dots and then follow the horizontal slant asymptote.
So how come it's not staying with that asymptote?
The question is, how come it's not staying with the well, that's because it's my wonderful sketching. It really should be staying with.
Like the little curve between the intersections.
Oh, the question was, how come this part here doesn't stay with the slant asymptotes? Good question. Slant asymptotes, like horizontal asymptotes, they only dominate at the extreme values of x's. They do not dominate in the middle. So I could, in theory, go like this. That is, in theory, possible, but not likely. But it's possible. So if you compare our sketch to the actual answer with Desmos, you can see that they look absolutely nothing alike. But as long as you label all the pieces, I can clearly see the slant asymptote, I can clearly see the vertical asymptote, I can clearly see your x-intercepts, I'll give you full credit. Even if your artistic ability are anything like mine, which is non-existent, I would give you full credit for this. All right, just make sure you label all the pieces. Okie dokie? So pretty easy concept. Same thing as yesterday. I'm adding just an extra layer. If the degree is bigger on top versus the bottom, you're going to have to divide and get a slant asymptote. Alrighty? All right. Let's take a look at the second case. Okay, Mr. Vo, you keep telling us to factorize just in case you can simplify, but we haven't been doing any simplification. What happens when you can simplify? Well, let's turn to Desmos. This last example here, you can actually simplify them. So let's see what type of weird, funky, rational function this guy produces when he can simplify. That's it. That's our picture.
It's a parabola.
It looks like a parabola, right? This isn't a weird, crazy, zigzag rational function. This looks like a parabola. What is going on here? Well, let's investigate. So we'll do that example. So what happens when you can simplify a function? So let's go ahead and sketch f of x equals, and that function was x cubed minus 4x squares plus x plus 6's all over x minus 2. Okay. So again, step 1, factorize everything, see if you can simplify. So the numerator is a 4-term cubic. I try to factor by grouping. Gosh darn it, it's not groupable. So what did we learn? How do we factorize something that's not groupable? You got to turn to your P's and Q's. I'm not going to show P's and Q's. That's not the point of this lesson. I'm going to assume you know how to do it. If you don't know how to do your P's and Q's, put that on your to-study list. But assuming you do your P's and Q's correctly, you're going to find out that the numerator factorizes into x minus 3, x plus 1, x minus 2. I'm just going to fast forward through that. Hey, gee whiz, look, the x minus 2 cancels. That's what happens. All right. And then we're left with x minus 3 times x plus 1. Now, we got to be very careful here. Notice my strings of equality. I am claiming that this guy here is equal to this guy here, which is equal to this guy here. Right? And my math is good, so that's not wrong. I didn't make any mistakes. But if this here is supposed to produce the same picture here, notice how the original function, there's some bad x values. what is one x values I should avoid using? I should avoid using the number 2, because if I use the number 2, it's going to put a 0 in the denominator. So if I'm claiming that this function is identical to this function, I need to prevent myself from using 2. So I need to put the domain restriction of x cannot be 2. And let's go ahead and just unfactorize, aka expand. So if you do repeated distribution, you're going to get x squared minus 2x minus 3. So big spoiler, that is why this rational function looks like a parabola, because he literally is a parabola. However, we have a domain restriction. This is the idea. Domain restriction produces what are known as removable discontinuities. That's just a $5 word of saying it produces holes in your graph. That's it. That's the only difference. So to graph functions that have cancelization, just graph the equation like normal, but you have to remember to put in the holes wherever the original domain restriction was. So I'll go ahead and graph this guy. Notice how he's just a regular quadratic. We sketched quadratics earlier. First thing you want to do is find the vertex. You can either use completing the square or just use that formula. X coordinate of the vertex is negative b over 2a. So that's negative 2 over 2 times 1, which is a 1. Right? Once you have the x coordinate of your vertex, you can do an xy table, starting with your vertex, and then just choose x values that are close to it. Say 2 and 3. And then you just plug it in. Now here's the other part where if you're going to make a mistake, this is where you're going to make a mistake. Kids like to go back to the original. We are done with the original. You never turn your back to it. It's long gone, right? You only work with your simplified version. So when I start plugging stuff in to get y values, I'm going to use this, or you can use the factored form because they're the same. So do not use the original, use the simplified version. So plug in a 1, you get a negative 4. Plug in a 2, you get a negative 3. Plug in a 3, you get a 0. So go ahead and make your coordinate grid. The numbers seem reasonable, pretty small, so I don't think I have to go too crazy here. So 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And then just plot them. 1 comma negative 4. 2 comma negative. Hold on a second. The original function said I can't use 2. But I clearly use 2 here, right?
Yeah.
So that means this is a legitimate point. 2 comma negative 3, that's legitimate. But because of my domain restriction, this will be a hole. So when you plot it, do not do a solid circle. You have to do an open circle when you plot it. Right. And then go ahead and do 3 comma 0 right there. That's only 1/2 of your parabola, so just use mirror reflection to get the other point. So I'm going to reflect this point here, and then reflect this point here. So do you guys agree that I got this point by reflecting my hole here? This point here is at x equals 0. Do I have any restrictions for x equals 0? No, so you got to keep it solid. One of the questions that was asked in the previous math class is, hey, Mr. Rowe, when we reflect the hole, does it stay open or closed? It will stay closed because we don't have any restrictions on the x-axis. So there's our picture. It looks like a parabola, but just with a little hole at 2 comma negative 3. You're probably going, but Mr. Vo, when I graph it in my graphing calculator or when I graph it on Desmos, I don't see the hole. And that is true. When you're graphing functions with technology, because of the continuous nature of real numbers, you're not going to see that gaping hole. But if you were to use your graphing calculator, hey, evaluate at x equals 2, it's going to give you a domain. It's going to give you a domain error. So that's sort of the limitations of technology. Technology will not show it, but as mathematicians, you have to know there's a gap there, right? So that would be the final answer, final graph. Okie dokie. Now, in this particular example, once we simplified, we ended up with a quadratic. The idea for case number 2 is you have to use the techniques of whatever resulting function you're left with. After I simplify, if it was a quadratic, graph it like a quadratic. After I simplified, if I'm left with a line, graph it like a line, y-intercept and the slope. After I simplify, if I'm still left with the rational function, you got to go through the whole process with the rational function. The idea is you graph your resulting function. You graph what's you end up with left over, but you just have to make sure your holes are in your graph. Okay?
Yep.
All right. That's it. That is the end of 3.6. That's the end of Unit 3. Sketching rational functions when the degree is bigger than 1, or degree is bigger on top, slant asymptotes. When you can simplify, you will have gaps, removable discontinuities.